I was looking through the logs from the LIGO experiment this morning, the Laser Interferometer Gravitational Wave Observatory. And the timeline of what happened on September 14th, 2015 is just, it's like a movie script.
It really is.
It's early in the morning. You've got these two huge detectors, one in Washington, one down in Louisiana. And for 40 minutes, just silence. In fact, a scientist, Robert Schofield, had just stopped a calibration test because he was just tired.
Which is such a crucial detail. I mean, if he had kept that test going, the whole system would have been offline.
It would have been in maintenance mode.
Exactly. They would have missed it.
But he didn't. He clocked out. And just 40 minutes later, the sensors pick up this thing that had been flying towards us for 1.3 billion years. A little chirp.
You know, it's so deceptive calling it a chirp. It sounds so small, so harmless.
Yeah.
But what that sound actually was, it was a cataclysm on a scale that, honestly, our brains just aren't built to handle.
I think that's putting it lightly. We're talking about two black holes, right? Each one maybe 30 times the mass of our sun, spiraling into each other at half the speed of light. And when they finally hit, the data shows they released 50 times the power of the entire visible universe.
In a fraction of a second. It's just
50 times the power of every single star in every single galaxy all at once.
Wow.
And the wildest part, digging into this material, is that it wasn't an explosion of light or fire. It was pure gravity. It literally, it shook the fabric of reality itself.
That's the key thing to grasp. It was a ripple in space-time, and by the time that ripple got to Earth, it was so faint. I mean, it moved the mirrors in LIGO by less than the width of a single proton.
Which brings us to the engineering, which I spent some time on because it's just insane. These detectors, they have to be isolated from everything. Trucks on a highway, miles away, ocean waves, even the thermal jiggling of the atoms in the mirrors.
It is the most precise ruler ever built by humanity. And that chirp was the smoking gun. Before that, black holes were, theoretically solid. We had some indirect evidence, but this was the first time we heard them. It was like astronomy went from a silent movie to a talkie.
So today we're doing a deep dive into these monsters. We've got a whole stack of research here, everything from the first theoretical papers back in the 1910s up to the latest data from the Event Horizon Telescope.
Yep.
We're going to look at what they are, how on Earth you find something that's literally invisible, and the part I'm really excited about, this architect theory. The idea that these things aren't just cosmic destroyers, but maybe the reason we're here at all.
It's a total paradigm shift. We used to see them as like glitches in the universe.
Yeah.
But the data now suggests they might actually be the load-bearing pillars.
But to get there, we have to go back, way back. Because even Albert Einstein, the guy whose math predicted them, he didn't believe they could actually exist.
He was a huge skeptic. He thought, sure, the math works on paper, but nature would find a way, a safeguard to prevent something that extreme.
It really shows you the difference between Newton and Einstein. I think that gets lost sometimes. In the old Newtonian view, gravity is a force, like a rope. The Earth pulls the apple down.
Right, a tether. But Einstein's general relativity just flips that on its head.
He said there is no tether. Mass, like a star, literally curves the fabric of space-time around it. The apple isn't being pulled, it's just sliding down the curve.
It's following the straightest possible path through a curved space.
Like a marble in a bowl. And the math says if you get enough mass in a small enough spot, you curve that bowl so steeply, it becomes a bottomless pit.
Exactly. And the guy who actually did that math has one of the most incredible and tragic backstories in science, Karl Schwarzschild.
The soldier scientist, I was reading about him. He literally solved Einstein's equations while he was stationed in the trenches of World War I.
It's unbelievable. He's calculating the curvature of space-time with artillery shells going off around him.
And he sends his work to Einstein from the front. He figured out that for any amount of mass, there's a critical size, we call it the Schwarzschild radius now. If you squeeze that mass down smaller than that radius, the escape velocity becomes faster than the speed of light.
And since light is the universal speed limit,
nothing gets out. That's the event horizon. We call it the Roach Motel of the universe. You can check in, but you can't check out. But really, it's weirder than that. Inside the horizon, space and time sort of swap roles. Moving forward in time is moving inward toward the center. You can't stop it.
That's a great way to put it. All paths, all futures, lead to the singularity. But Schwarzschild died not long after that, and for decades, this was just a mathematical ghost. Nobody thought nature actually built these things.
But it does. The construction method is stellar suicide.
Right. Specifically, the death of really big stars.
The physics here is so cool. A star is just a constant battle, right? Fusion pushing out, gravity pulling in. It burns hydrogen, then helium, all the way at the periodic table. But then it hits a wall.
Iron.
Iron is the ash of fusion. Yeah. Before iron, every fusion reaction gives you a little extra energy to push back against gravity. But fusing iron actually costs energy. It's a heat sink. So the second a star's core starts making iron, the furnace doesn't just turn off, it goes into reverse.
The support beams just vanish instantly. And gravity, which has been waiting for millions of years, it wins. The core collapses, the outer layers rebound in a supernova, and if that leftover core is heavy enough,
You get a singularity, a point of infinite density in zero volume.
a puncture in space-time.
So, okay, let's get visceral. What's it like to fall into one? The sources describe it, and it's horrifying. First, there's spaghettification, which is a very cute name for a terrible, terrible death.
It's just tidal forces, really. If you fall in feet first, the gravity pulling on your feet is way stronger than the gravity on your head. And around a small, stellar mass black hole, that difference is enough to literally stretch you into a noodle of atoms.
But the visual part is what gets me. Because of how light bends, if you were hovering just outside, you could theoretically see the back of your own head.
Gravitational lensing, yeah. The light from your back would orbit the black hole and come right back to your eyes. You'd be, like, wrapped in your own image.
And the time dilation. If I stay safely on the ship and watch you fall in, I never actually see you cross the event horizon.
No, you wouldn't. To you, my image would get dimmer and redder, and I'd appear to slow down until I just froze at the edge. I'd fade away, but be frozen there forever from your perspective.
But from your perspective.
My watch would tick normally. I'd cross the line without even noticing a bump right up until the spaghettification started.
So we have these invisible, time-bending traps, which raises the question astronomers had in the 60s. How do you find a black cat in a pitch-black room?
You listen for the furniture, it knocks over.
Or the analogy from one source was looking at Yankee Stadium from the outside. You can't see the game, right?
Yeah.
But you see the traffic, you hear the roar of the crowd. You infer the game from the chaos around it.
And in space, that chaos is usually a star being violently thrown around.
Which brings us to Cygnus X1, the first big suspect. You had this huge blue star, and it was being whipped around in a circle every 5.6 days. It was dancing with an invisible partner.
And that invisible partner was sucking gas off the visible star, heating it up to millions of degrees and blasting out X-rays. That was the roar of the crowd.
But even then, people were skeptical. I was reading about the famous bet between Stephen Hawking and Kip Thorne.
Oh, yeah.
Hawking bet against it being a black hole. He called it his insurance policy. He figured if black holes weren't real, his life's work would be a bust, but at least he'd win a magazine subscription.
He eventually had to pay up, though.
He did, because of a researcher named Mark Reed, who used parallax. This is the finger-winking trick, right? You hold up your finger, close one eye, then the other, and it seems to jump.
Exactly. Reed used radio telescopes all over the globe to look at Cygnus X1 from opposite sides of Earth's orbit, like closing one eye in the summer and the other in the winter.
And by measuring that tiny jump, they nailed down the distance, about 6,000 light-years away. And once you know the distance, you can figure out the mass. It was 15 times the mass of the sun. Way too heavy to be a neutron star.
It had to be a black hole. Hawking literally broke into Thorne's office to sign the concession letter he'd framed on the wall. They were real.
So that's the small ones, the stellar corpses. But then the research shifts gears completely to talk about what's hiding in the middle of galaxies, the supermasses.
A completely different beast. We're not talking 15 suns. We're talking millions, sometimes billions of solar masses.
And we found these things by accident, almost, by looking at quasars. In the 60s, astronomers saw these star-like objects that were impossibly bright. It was a guy named Martin Schmidt who finally cracked the code.
Right. He looked at their light spectrum and he realized the hydrogen signatures were redshifted. I mean, heavily redshifted.
Which means they're moving away from us really, really fast. And in an expanding universe, speed equals distance. Schmidt realized these weren't stars in our galaxy. They were billions of light years away.
And to be that bright from that far away, the only engine powerful enough is a supermassive black hole just gorging itself on gas. A quasar is the scream of a black hole as it eats.
Which leads to the really uncomfortable question. If other galaxies have these, do we?
This is Andrea Gheza's work. It's just stunning. She spent more than 15 years tracking stars right at the heart of the Milky Way.
And the tech is amazing. They use something called adaptive optics. They literally shoot a laser into the sky to make an artificial star.
Measure how the atmosphere blurs that laser light, and then use a mirror that can change its shape hundreds of times a second to cancel out the blur. It's like noise-canceling headphones for starlight.
And with that, she saw it. Stars moving at 10 million miles per hour doing these insane hairpin turns around. Nothing. An empty spot.
And using basic orbital mechanics, she calculated the mass of that nothing. The answer came back 4 million times the mass of the sun.
Sagittarius A star. Sitting right there in the dark at the center of our own galaxy.
And follow-up surveys prove this isn't an anomaly. Pretty much every major galaxy has one.
Okay, but here's the part of the research that I got stuck on. A 10 solar mass black hole. Okay, a star dies. I get that.
Yeah.
But how do you make a billion solar mass black hole?
Yeah, you can't just eat your way there from a small start.
Right. The papers talk about a black hole shredding a star that gets too close. A tidal disruption event. But that's like trying to get fat by eating one grape every couple of years.
And there's a speed limit. It's called the Eddington limit. If you try to feed a black hole too fast, the material falling in gets so hot that the radiation pressure literally blows the rest of the food away. It chokes on its dinner.
So there's a timing problem. We see these massive quasars when the universe was super young, only 500 million years old. There just wasn't enough time for a stellar mass seed to eat its way to a billion suns.
It's a paradox, unless they didn't start small.
The direct collapse theory.
This is the leading idea. In the very early universe, you had these enormous, pristine clouds of gas. Now, normally a cloud like that would cool down and break apart into thousands of little clumps that form stars.
But what if it didn't?
What if conditions were just right? Maybe it was being kept warm by radiation from other galaxies, so it couldn't fragment. The entire cloud, maybe 100,000 times the mass of the sun, would just collapse all at once.
So it skips the whole star phase.
It's born huge. It gets a massive head start. And if you start with 100,000 solar masses, getting to a billion in time for those early quasars is much more plausible.
Which brings us to the last part of this deep dive, and honestly the most profound part, the architect theory. Because we see this strict relationship, the bigger the galaxy's central bulge, the bigger its black hole. They grow together.
It implies a symbiosis. The black hole isn't just a parasite living in the galaxy, it's a regulator.
A thermostat for the whole galaxy.
Exactly. When a black hole feeds, it doesn't just swallow stuff, it blasts out these enormous jets of energy and particles.
We see those with radio telescopes, yeah, stretching for thousands of light years.
Well, that energy heats up all the gas in the galaxy, and hot gas can't cool down and clump together to form new stars. So if the galaxy starts making stars too quickly, the black hole gets more food, it fires up its jets, and it shuts down the star factory.
It stops the galaxy from burning itself out. It keeps things stable.
Without that feedback loop, galaxies might just be these giant chaotic fireballs. The beautiful, orderly spiral of the Milky Way might only exist because of the monster in the middle keeping everything in balance.
So in a very real way, we might owe our existence to Sagittarius A star.
We very well might.
And that brings us to today. We've got the Event Horizon Telescope taking that incredible picture of the black hole shadow. We've got LIGO detecting collisions almost every week now.
We are absolutely in the golden age of black hole astronomy. We are finally, truly seeing the invisible.
But I want to end on one final thought from the source material that is, well, it's heavy. The dark era. We know the universe is expanding. We know stars are all going to burn out eventually. So if you play the tape all the way forward, what happens?
It's the ultimate end state. Stars stop forming. The ones that exist die out. Galaxies go dark. And all the while, the black holes keep growing, sweeping up all the cosmic debris. Eventually, the universe will be almost nothing but these giant, isolated black holes sitting in total darkness.
A universe of ghosts.
For a very, very long time. Even black holes evaporate through Hawking radiation, but that takes an unimaginable amount of time. So yeah, the long-term forecast is cold and dark.
That sounds incredibly depressing, but reading about it, it actually made me feel kind of lucky.
How so?
Well, think about it. We happen to be alive in this one brief, shining moment in cosmic history when the lights are on. We've got stars, we've got heat, we've got galaxies. We're living that tiny, perfect window between the fiery beginning and the cold, dark end.
That's a beautiful way to see it. The darkness of the future doesn't cancel out the light of the present. It just makes it that much more precious.
Exactly. So next time you look up at the night sky, just remember, you're looking at a limited time offer.
Enjoy it while it lasts.
Thanks for diving into the abyss with us on this one. I think I need a coffee after that.
I think we both do.
See you in the next deep dive. Keep looking up.